All right, so welcome to the last day of physics class. Woo, we finally made it. We have just one more topic we need to talk about along the lines of the second law of thermodynamics, but we're definitely in the home stretch. We still have a little bit more, of course, to wrap up. There's some more homeworks. There's the final exam and things like that. But let's go ahead and take care of business here and knock out the last topic, which is entropy. Now, entropy is just another characteristic, another state function. So basically what I mean by that, it's like temperature. Your temperature is based on your current state, right? And internal energy is based on your current state. Entropy is another thing that's based on your current state. It can change as you move from one state to another. But if you come back to the same state that you were in before, you've got the same entropy that you had before. Okay, so same thing like temperature. You can change your temperature and do all kinds of stuff, but if you return back to the initial state, your temperature is the same. So it's just yet another one of these things that describes an object, a system, but it's one you may not have ever seen before, so it might feel a little bit weird at first, but it's just yet another state function. So let's get to describing it, defining it. So I'm going to go ahead and go to the board. All right, so entropy, we use the letter S or entropy. Probably S and not E, because E is already part of energy and stuff like that. Okay, but we use the letter S. Now, how we define entropy is really a change in entropy. Okay, we define that change in entropy, delta S, to be Q over T. So Q is your heat, the heat that happens in this process, divided by the temperature at which the process occurs. Okay, so again, this is the heat in a process, and this is the temperature at which it occurs. It's very important that this is in Kelvin. Okay, so it's an absolute temperature, but this is how we define entropy. All right, now here's where it gets a little bit interesting when we actually want to do a calculation. Okay, well, let's just think about this. Think about some of the processes we've seen. If we have something that's adiabatic, so remember adiabatic, this means that there is no heat. So in an adiabatic process, the change in your entropy is 0. Nothing happens. So we go, okay, cool. That's nice and easy. So you think about the other processes. All right, what if it's isothermal? So isothermal, of course, means the temperature is constant. Well, if the temperature is constant, then it literally is just going to be just Q over T. So we would look at what the change in the heat is, or what heat is applied over that temperature. So it could be positive, it could be negative. We've seen examples of isothermal processes that have positive heat and those that have negative heat. You may recall when we were talking about the Carnot cycle, In the Carnot cycle, there were the two parts where we had heat exchange, and one was positive and one was negative. Okay, so that would be isothermal. So then what if we're in one of the other ones, like isobaric? And I'm actually going to put isochoric here as well, because both of these have a potential issue. Do you see what the problem is with how we've defined entropy if we've got something that's isobaric or isochoric? Well, I'll tell you this, it's not the heat calculation. We know how to calculate that.
Isn't it like Pervner or something like that? Because isobaric relates to pressure. And
So isobaric, it's pressure, it's same pressure. But here's, excuse me, here's really the problem with both of these, is that the temperature is changing. We're not actually at a constant temperature if we do either isobaric or isochoric. So we have to figure out how we're going to deal with that. Well, excuse me, what we're going to do is what we always do, which is let's break it up into a whole bunch of sort of instantaneous processes that are the same temperature. They're just really, 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 really small time length or whatever, and then add all those up. Well, that of course leads to an integral. So really, the way that we define this is that the change in the entropy is going to be the integral of dq over t. So we're just going to think of it as a whole series of tiny little steps. Add up, add them all up, and that leads to an integral. So we're going to start in, I'm going to put like an I and an F here. So we're going to start in our initial state, and then we'll go to the final state, and we'll do an integral of dq over t. So one more thing that I do have to mention is that this formula, this is assuming that we have a reversible process. And we saw last time that reversible, that's a, well, theoretical. Everything really is irreversible or irreversible, but we can't use these formulas. Except we kind of can. And I'll get to that in a second. All right, so let's look at a couple of examples how this plays out. So let's do this first. Let's take some ice and let's melt it. Okay, we're going to melt 1 kilogram of ice. And I want to find out what the change in the entropy is. So if we take a block of ice and we melt it, what's our entropy? All right, so for this, good news, this one is isothermic. The temperature doesn't change, right? Ice that's melting is at 0 degrees C the entire time. The water is also at 0 degrees C. It doesn't start changing temperature until all of the ice is melted. And then it turns into water and we go. Okay, so this is good because this tells us that the temperature is 273 Kelvin. All right, so far so good. So that's going to be on the bottom, and it is constant, so we don't have to worry about it, which means since it's constant, we don't actually need an integral. We can literally just look at what is the change in Q, what was our heat, and divide it by our temp. All right, so how are we going to figure out how much heat is required to melt 1 kilogram of ice? What formula are we going to need to use?
Formula for latent heat of melting. There's a different term for it, I think.
There is, it's fusion. Latent heat of fusion. Okay, good. So we need the latent heat of fusion. And the way that this works, we take the mass times that latent heat of fusion. All right, so let me go find the latent heat of fusion of ice water. I don't know that one off the top of my head, but I've got a book here that will give it to me. I just got to find it here. Probably should have looked this up earlier, huh? There we go. Okay, so the latent heat of fusion is 334 times 10 to the third. We're going to take 1 times 334 times 10 to the third. And then we're going to divide it by the 273 Kelvin. All right, so go ahead and take your calculator, calculate that real quick. So 334 E3 divided by 273 times 1. And what we get is a change in entropy of 1,223.4. And the units on this are joules per Kelvin, right? Heat is in joules. So we have joules per Kelvin. So you melt 1 kilogram of ice, and there's been a change in entropy of just over 1,000 joules per kilogram. All right. So now let's take that water, because now it's 0-degree water. Let's bring it up to boiling. So our next step is going to be take that ice or that water. So let's raise that 1 kilogram of 0-degree sea water to 100 degrees C. Oh, excuse me. There must be something about this time of day, because you notice how I'm always a little hoarse and I'm kind of like coughing. Happens every day at the start of this class. None of the other classes, just this one. So
Maybe it's because you've been talking for a while.
yeah, maybe. Or I don't like you guys, or I'm allergic to somebody, or something. Not enough beer. It's probably not enough beer.
Probably me you're allergic to.
All right. So let's see what we find here. Now, in this case, our temperature is changing. So we're not going to be able to just plug in our heat and all that. But let's think about how heat works when we're raising temperature. So what formula do we have there for our heat? So latent heat is when you change state. What's the heat that changes temperature? Nothing? I'm looking for a specific term.
Energy? No, that's...
So heat is a form of energy, but there's a specific term for the kind of heat that changes temperature, right? Like latent heat changes.
Oh, specific heat.
Yeah, there you go. I was being tricky. I said specific a couple times, trying to trigger your memory. So it's specific heat. So for specific heat, that was Q equals M times C times delta T, right? So the times the change in temperature. But we need now differential. So we're going to get dq is M times C times dt, which means our change in entropy is going to be the integral of M times C times dt over T. And we still need to put on our bounds. So the initial temperature is going to be 273 because we were starting at the freezing point. And then we're ending at 373. So M is the mass. That's going to be constant. C is the specific heat of water, which is also constant. And so it's only T that varies. And so what we're going to get, that MC, we can pull that out. But we integrate 1 over T. That's going to be the natural log. So we're going to get natural log of 373 minus the natural log of 273. All right, excuse me. So now let's put in our value. So we had 1 kilogram. The specific heat of water is 4,190 joules per kilogram, Kelvin. And then we have to evaluate this natural log. I'm going to go ahead and just make it a little bit easier to calculate, make it one fraction. All right, so you run your numbers there, and you get 1.31 times 10 to the third. So notice that it's just slightly more, but entropy has increased again. By heating up that water, we've increased its entropy. Okay, well, let's do one more thing with this. Let's boil this water. So now that we've got it up to 100 degrees, let's turn it all into steam. Okay, so this is the third. So now we're going to convert the 1 kilogram of 100 degree C water into steam. All right, well, now we're back at an isothermal process. It's always 100 degrees C. So we can go back to just doing this non-calculus question. So we're going to get delta S is equal to the heat, which is going to be M times LV. So now we're going to use the latent heat of vaporization. We're going to multiply that by the mass and then divide by T. Okay, so let me look that up here real quick. So the latent heat of vaporization for water is 2.256 times 10 to the 6th. So we're going to have 1 kilogram times 2.256 times 10 to the 6th joules per kilogram divided by, now we're going to use 373 Kelvin, right? Because we're at the boiling point. So we have to add on that 100. All right, so let's take our calculator. And when you do this computation, I get 6.05 times 10 to the 3rd. Let's just go ahead and rewrite this as 1.22. That way we have some commonality between these. All right, so just take a look at the change in the entropy as we go through these. We get different numbers because there's just a different amount of heat and different process going on. But you notice that they're all positive. We added to the entropy in all of these processes. And there's actually a pretty significant difference between the boiling and the other two, right? The other two were pretty similar. This one's, you know, over 4 times as much as just raising the temperature. But if you were to take that full kilogram and convert it from ice to steam, using the 2 phase changes and then the heating up, you're going to get a total of around 8,500 joules per Kelvin as your change in entropy. All right, well, that's how you calculate them. That's all you got to do to calculate it. But the question then really is, what the hell does it even mean? What is entropy? What does it measure? And what does it have to do with like the second law? All right. Well, before we get there, I just want to mention one more thing, and this is kind of interest. Well, first of all, what if we'd gone the other direction? What if we had taken this steam and cooled it down and turned it into ice? What would the change in entropy have been? Like, what if we'd gone backwards? What do you think would have happened to the entropy?
The entropy change would be the same, but it would be like a different sign.
Yeah, it would just be negative. So if we are increasing the entropy, as we raise the temperature, we're going to decrease the entropy as we lower the temperature, or it's going to go down if we go from steam to water or from water to ice. Okay. All right. So one other thing I want to mention is this. What if it's a cyclic process? So think about what I'm talking about, a cyclic process, like when we were talking, say, about the Otto cycle or the Carnot cycle or something like that. Well, in a cyclic process, your change in entropy is 0.
Would that sort of thing happen? Oh, sorry.
No, that's okay. Go ahead, Jacob.
Would that sort of thing happen when something is like in a supercritical state, like when it's changing in between fluid and gas, like to the point where they're not even really distinguishable? I mean, liquid and gas, sorry.
So a cyclic process means you're coming back to where you were before. you're returning to the same state that you started. So that would be more like we had ice, we melted it, and then we refroze it.
Okay.
Okay, or like when we were talking about the Carnot cycle, we're going to expand our gas adiabatically. Then we're going to change the temperature, right? Lower the temperature. Then we're going to compress the gas adiabatically and then change the temperature to get back to where we started. If you follow a cycle, you're going to get back to where you started, and your change in entropy is going to be 0. And the reason behind this is because S is just a measure of your state. And so if you return to the same state, your entropy is 0. But it's even a little stronger than that. Like if we were to draw out, here's a PV chart, let's say, PV diagram. Remember when we were doing things like this, right? So this is one that if I started, let's say on this lower left corner, or sorry, lower right corner, and I go through this process exactly once and come back, there's no change in entropy. If I look at this one versus any of the other points, there could be a change. And that change is going to be determined by the formula, the integral of the dq over t, applying it to whatever our processes are. So like if it was isothermal, well, then you can just go ahead and do q over t. If it's adiabatic, it's 0, right? But those we'd have to do individually. But if I told you that we went all the way and got back to where we started, then what we know is that that's nothing. There's no change in your entropy. So next year, when you guys are in vector calc, you're going to learn about these things called line integrals. And you'll see this whole like closed cycle thing giving you 0 again. And we'll talk about it more at that point. I think that's going to be me. I think we've got it set up that I'm going to be teaching diffie-qs, or not diffie-qs, vector calc. So I will probably remember when we get there to bring this up again. If I don't, maybe at least one of you will remember, and we can have a chat about entropy again when we talk about line integrals. Okay, but here's the other thing that's sort of important about this. It's not so much if you do a cycle, you're back to 0. I mean, that's useful. It makes it really easy to calculate entropy if you've got a cyclic function or a cyclic process. But even more important is that not only do you get this, but if you were to look at the change in entropy going from one state to another. So let's say we're going to go from state number 1 to state number 2. Since entropy is a state function, it only depends upon where you are, you're going to get the same delta S, the same change in entropy, regardless of the path. And we actually did this with energy. I don't know if you remember that, but like when we were looking at the change in energy and the heat and work from the first law, it totally didn't matter how we went from one place to the other. All that mattered was we ended at that spot. And that's the same thing here. So even if we were just take like the straight line process, or an adiabatic process, or a combination of isobaric and isochoric, and it doesn't matter. You're going to get the same thing no matter how you get there. Now, I don't know if you can see why this is nice, but what this allows us to do is to think about what's the easiest one to calculate. What's the easiest one to calculate from state 1 to state 2? that's the one I'm going to pick to do, even if that's not the one that's given to me. Another big advantage to this is, what if you don't have a reversible process, right? Remember I said that delta S over T, or sorry, delta Q over T, that only works if it's reversible. So if it's irreversible, what you do is you look at your states and you find a reversible process in between the two. Calculate your entropy that way, and then you're good to go. So it's kind of nice. Entropy as a state function allows us some kind of workarounds for calculation, make things a little bit easier. All right, but what is entropy? What does this actually mean? What's going on with it? All right, well, entropy, for lack of a better word, is disorder. So if you increase entropy, you are creating more disorder. So that's really what it means. And I want you to think about what we just did when we were looking at going from ice to steam. So let's just start with ice to water. We saw that there was an increase in entropy. Do you see why there was, or where the increased disorder was? What gets less ordered when we go from ice to water?
The fact that all of like none of the molecules are in like a crystal structure anymore, like they would be in ice. They're all like floating around and bumping into each other.
Yeah, that's exactly it, right? As a solid, molecules are nice and ordered by a lattice structure of some type. There's nice rigid bonds, there's order. Okay, well, when it's water, they're still bound together-ish, but they're much weaker. There's more ability for them to move around. Right? The situation's more fluid. Sorry. So there's definitely less order. Okay, so now let's think about going from water to steam. Same story, right? Because now as it's steam, the individual molecules aren't bound to any of the other molecules, right? They're just kind of out doing their thing. And so we've definitely led to more disorder. So then what about the heating of the water? So we still have water the whole time. So it's not like all the bonds are being broken. But think about what it means when we heat things up. We're increasing their internal energy, their kinetic energy. So they're moving around more and jiggling and all that. And they're starting to pull on each other and trying to get away from each other. And so it's becoming more disordered. So that's really what entropy is. Greater entropy means greater disorder. All right, well, let me change these here, because I want people who are watching the video to be able to see me now, because I'll be using my hands a bit. Okay, so entropy is really a measure of disorder. Greater entropy is greater disorder. And here's the deal about the universe. The universe wants less order. It wants things to be, I was going to say chaotic. It's not quite the right word, but the universe doesn't want order. And this is like a probability thing. Here's what I want you to think about. Suppose that I've got 10 quarters that I'm going to, toss, 10 coins I'm going to toss, heads or tails. All right. You can probably just have a decent understanding of this if you just kind of think about it. How likely is it going to be that if I toss 10 coins and that they're all fair, 50-50 shot, how likely is it going to be if all 10 show up as heads? Would that surprise you?
Oh yeah, that'd be.
Yeah, and the same thing if they were all tails, right? Like I take 10 coins, I throw them up in the air, we watch them hit, and we look at them. If they're all 10 heads or all 10 tails, I'm going to be shocked. Now, I would still be shocked, but not as shocked if it was, say, 9 heads and 1 tail. I'd still go, ooh, that was kind of cool. If it was 8 and 2, yeah, kind of interest. 7 and 3, I might notice. 6 and 4, probably wouldn't bat an eye. 5 and 5, yeah, that seems about right. Right. So if you look at like the probabilities, you would see that it's very much more likely for these random events to be such that we end up in that just about the same either way. Okay, well, think of this as order and disorder. Getting 10 heads, that's very ordered. And very ordered is very rare. What's much more likely is to get this disorder, this, how would you even know which of the 5 were the 5 and all this, right? It's just sort of, even if you just look at the numbers, the different possibilities, it's way more likely to have that occur. Now, this is what's going on with entropy. If you look at the microscopic, what's going on with all these particles, it's pretty math intensive. And when you get to modern physics, this will make a little bit more sense. But everything is probabilistic. Everything is based on probabilities. Everything in physics. We're not used to thinking that way because in the macroscopic, in the big picture, things aren't probability based, right? We've got rules. We see what the rules are. We know what's going to happen. But when you look really, really closely, everything is based on probabilities. Well, because it's based on probabilities, it's not as likely to get the everything is heads, everything is tails. You're much more likely to be somewhere in the middle. So that's what I mean when I say the universe wants, not really want, right? I mean, it might have consciousness. I don't know, but I don't. But it's the nature of the universe, just the nature of the probability ness of matter to want to be in this not ordered, just sort of everything is nice, evenly mixed. All right, so here's the tie-in then to the second law of thermodynamics. The second law can be written in a third form. So we've already seen a couple forms of it, right? The first form was the engine form, that if you are using heat to produce work, you cannot get 100% efficiency. We saw the refrigerator form, which was basically energy is not going to spontaneously go from colder to hotter. You got to do some work to drag it along. Well, here's the third form. The third form is that the entropy of the universe is always increasing. It's actually a really simple thing to say. But the entropy of the universe is always increasing. So, and I'll write this on the board in a second, but basically that's just saying that delta S is greater than 0. It can be 0, obviously, if there's no process going on. But in general, the change in entropy of the universe has to be greater than or equal to 0. It also turns out that you can say that for a closed system. If you've got a closed system, you have to have a net balance. But usually we talk about it as universe. So think about this. When we were heating up the water, we had positive change in entropy. So you're like, okay, cool, no problem. That follows the second law of thermodynamics. But what if we cool it down? Because now, like, when I asked that, and Jacob said, well, now it'd have a negative number. If we were to take water from 100 C and lower it to 0 C, there's a decrease in entropy. All right. So you might go, but wait a minute. So then the second law doesn't matter. No. What we have to remember is that the change in the entropy of the universe has to always be greater than or equal to 0. So think about what that means. If we just created some order by cooling the water down, something else had to get more disordered. Well, this is basically that idea of there's going to be some work that has to happen. There's going to have to be some loss of efficiency. That's where all this goes. And that's why this tracks, is that overall in the system, there has to be an increase in entropy. So think about this just for a minute. Like, think about you as a person, as a creature, as a structure. You are very ordered. I know sometimes you might not feel like you are, but you are very ordered. To get all of the molecules that make up your body in exactly that right form to produce the cells that then make the skin and the hair and the bones and everything else about you. There is a lot of order that has to happen there, right? When you die, though, think about what happens when you die. Your body falls apart. It decomposes, right? In that process of decomposing, now you're increasing the energy or the entropy of the system. But you getting ordered loses entropy or gains entropy for the universe. It loses order. And where that comes in is like the eating of your food, for example, right? Think about what happens when you eat food. It's got whatever its form. You start breaking it down. You chew it. Your saliva starts working on it. Gets into your stomach, and now the stomach acids and all that start breaking it down. Your body starts absorbing it and all that. But there's always a loss. There's always a loss. And so even though you're getting that food to help your body maintain order, it was at the expense of more order went away. So we're kind of transferring some of the order from out here into our body, but it's not all of it. Some of it gets more disordered. So you may remember that when I was kind of giving you the preview of this last time, I said that the universe is, the future of the universe is kind of bleak. And that's kind of what I'm getting at here, because eventually, if every process is going to increase entropy, or best case, keep it where it is, eventually the disorder of the universe is going to win out, and we're not going to have anything that's ordered. It's all just going to be randomly out there disordered. All right, well, so for me personally, my personal philosophy, well, I see this every day, actually, and you guys probably do as well. Think about this. So you kind of get it in your mind, I'm going to clean up the house. Right? So you clean up the house, everything's put away, it's beautiful. Yeah. It doesn't take very long for the house to get chaotic again, especially if you live like I live. Yeah, I should just show you my desk. I start off with it nice and neat pretty much every day. And by the end of the day, Actually, I'll show you right now.
Oh, that's
All right,
like
so I just
the
turned
chaotic
on my
room
camera here,
of my room.
and you can see there's a bit of chaos going on here. But I promise you, like at the start of the day, these papers weren't here. This was all nice and neatly stacked. I mean, these pens were actually over in this tray, and there weren't these food dishes, and so just through the natural course of my existence, I've added a bit of chaos, right? And is that you, Ian, who just said something about your room?
It's like, yeah, it's like making your bed, right? It's like you wake up and then your bed, you like get out and then it's a mess and then you have to make it. Same
Yep.
with like cooking. There's just like everything,
Everything.
Everything mess is made.
So you can imagine how popular I was with my parents when I learned about entropy.
Oh yeah.
Because
I
then
loved
when
you.
there was can you clean the room? I'd be like, why?
Cleaning's ultimately futile. It's just resisting the natural order of the universe, Mom.
Right. And not only that, by me ordering my room, cleaning up my room, I'm actually creating more disorder elsewhere. How selfish is that,
Uh,
Mom? Are you really so selfish that you would trade your own comfort for chaos for everyone else? I mean, yeah, like that's,
You really want to speed up the death of the universe and make me clean up my room?
yep. So I'm thinking that I took physics, or I learned about entropy in physics probably when I was about 16, right? Plus or minus. Ooh, you don't want to put that into the hands of a 16-year-old, because then, oh my God. But yeah, the argument just finally turned into just clean your damn room because I'm your mom. I'm like, okay, that's fair, right? Before I beat you senseless. Okay, fine. Um, but yeah, so if you think about it that way, it's like, all right, so all life and existence is meaningless. Or as Jacob says, it's a futile effort to delay the inevitable. So um, yeah, it is. However, we can locally, right? You can decrease entropy locally. It's okay. Like there are plenty of instances where we make negative delta S, but just realize that overall, that's a losing battle. So the entropy form of the second law is basically the same as the others. It's just stating it in a different way, right? In terms of order and chaos and whatnot. All right, so there's entropy. And it really just comes down to the fact that everything is probabilistic. I don't know if you've ever heard the quote. Albert Einstein, he made the quote, said something, I'm paraphrasing, but it's pretty close. Something along the lines of God doesn't play dice. And he made that statement because when they were discovering all this quantum mechanics stuff 100-ish years ago, and probability started kind of coming into play, he didn't like that. Didn't sit well with him, because it's like, how can everything just be completely random? And especially if you're if you're religious, and the idea of God creates and all that, so all of a sudden he's like, no way, it doesn't, God doesn't play dice. Well, God may not, but the universe definitely does. And I can't wait for you guys to get to modern physics, and see how everything is based on probabilities. How, for example, there is a non-zero probability that if I take my hand and I slam it against the wall, non-zero probability that my hand will go through the wall without breaking the wall. Like literally just sort of do one of those like teleport kind of deals.
It's non-zero. It's crazy low, like so low that it might as well be zero, but it's not zero. There's a non-zero probability that by the time I'm done making this statement, that my entire body shows up on the moon. Like legit. Mathematically, there's the possibility that I all of a sudden just spontaneously teleport to the moon. It's not going to happen. I mean, if it did happen, first of all, sweet, I finally made it to the moon. Second of all, that sucks because I'm dead. Not just because I don't have like a suit on. Even if I had a suit on, I'm not going to magically teleport back. It's such a weird, it would be such an unusual occurrence that it happening twice. That's when we're definitely playing with loaded dice, right? But yeah, so you'll find that everything is based on probabilities. The probability model makes everything reasonable, and that naturally leads to this idea that the entropy of the universe has to be increasing, which honestly is one of the things that sort of made the probability model or helped support the probability model. Like anytime in physics, if you come up with a new idea, not just physics, but science in general, anytime you come up with a new idea, the more that it links into previously established ideas, the better, right? If you come up with a new thing that needs all kinds of exceptions for all these other things that don't quite fit it, that probably means you don't have a good model. But if you come up with this new model and everything just sort of tracks, and you go, oh yeah, see, that explains what we saw with entropy, and oh yeah, and that explains what we see with gravity, and oh yeah, that's what, right? Then you can start going, oh, maybe this model is good. And this was definitely one of the things that supported the idea of matter following probabilities. So, all right, well, I'm going to pause here. Let's take a break. Okay, so Jacob, you told me you had a question. What's your question?
Is that the same sort of like principle that's like behind like the infinite improbability drive concept from like the Hitchhiker's Guide to the Galaxy, or?
Okay, so when we start talking about things from fiction, what their actual motivation is, obviously I can't speak to. And I actually know nothing about Douglas Adams, so I'm not sure if he's got like a scientific background and therefore used a little bit of that behind it. So I don't know exactly how to answer that question.
I'm sorry, I
No,
should have
that's
asked if
okay.
you had read it first.
Well, no, I have read it, but it's been a long time, honestly. Um, I mean, basically, how this plays out is that um, so this is like major spoiler alert, by the way. So when you get to modern physics, if it's not me and it's Kathy, pretend like you've never heard this before. All right. Basically, what happens is that everything has a most likely location to be. All right. So like if we're going to talk about an electron, let's even go in like in a hydrogen atom. So super simple. We just have one electron going around one proton. So that electron, we never know exactly where it is. We have an idea of where it's likely to be, but we don't actually know where. So there's a probability model that describes where it can be. And part of that probability model allows for that particle to be 1,000,000 miles away. Now, the probability of that is very, very low, but exists. And so since it's like a probability thing, and there's a non-zero probability, then that electron could actually be 1,000,000 miles away, right? Now, when I talk about like all of me managing to go to the moon, so now we're talking about all of the particles that make me up are using or are all existing in that very unlikely location all at the same time, right? And so that's why I can say with virtual uncertainty that that will never happen. However, it could, right? Just like I could take this pen and let go of it and it might not drop. Now, if that were to happen, that would freak me out. And I would hope to God that I was recording it at the time so people could see, and even better that somebody else was here, could see that there are no strings or anything, because that's that 1 in billions to the 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 Google probability that that would happen, chance that that would happen. And I would never be able to replicate it. Not never, right? I mean, there's still a non-zero probability that it could happen twice, but we all know that that wouldn't occur, right? So anyway, to get back to your question, so give me a little more detail about this engine.
So like the theory behind it is that it generates a field where everything is like infinitely improbable. So like I don't really know how if I'm explaining it the best, but like so because it's in an infinite improbability field, everything that's completely unlikely to happen does happen. And so like the principle behind that is like it sort of I think it's the same sort of thing, but that's what I'm asking about is like
okay, so
it uses that sort of concept of like spontaneous teleportation of particles or whatever based on the
okay, so probably the idea behind it in the book is that they're able to manipulate the wave equation, and so kind of messes with the probabilities and makes it so that those really unlikely things now are quite likely. I have no idea how you could even pretend to do that, like from an engineering standpoint, but there could be a little bit of that behind it. So.
All right, thanks.
Oh yeah, but as always, I love the crazy questions. Any other questions kind of about what we've been talking about with entropy and all that? No? Okay. Well, so let's just sort of plan for the future and what's going on. So I already stated, I think on the record, if not, I'll put it on the record now, that the final exam is actually on Monday. So Monday of finals week, and as you guys know, that's it, right? We don't have any class or anything. It's just the final exam. Not everybody is going to be required to take the final. You may remember from the syllabus that it states that if you've done all the homework, at least 50%, and no more than one of them are late, then you do not need to take the final exam. You still may, right? But you don't have to. But if you do take the final exam, there is the possibility that your overall grade will lower, right? So like if you tank that final exam, it could hurt you overall. So that's something that you should definitely take into consideration as you're trying to figure out whether or not you want to take it. Now, there are some people that do have to take it, I'm not naming names, but there are some people that do have to take it. So there will be an exam written and ready. So if you're one of those that has the option, don't look at it as, oh man, maybe I shouldn't do it because then Bruce is going to have to write it. Or no, don't. That's not part of it at all. You just need to, if you feel like you want or need to take it, that's totally up to you. Okay, so regardless, if you take it, it will open up at 3:00 on Monday. And you will have 2 hours to take it, and I'll add in that half hour of grace time for technological issues or whatever. So it will need to be submitted by 5:30, and that 5:30 is a hard and fast 5:30. Okay, so don't push it. Remember, the idea is I'm giving you plenty of time to deal with technology. Don't think of it as, oh, great, I've got an extra half hour and I can rush and try to upload. That's not what I suggest at all. Okay, so But anyway, so if you want to take it, it will be available starting at 3 o'clock. If you are one of the people that have alternative testing arrangements, please just let me know ahead of time what you would like to do there if you want to change the time. If I don't hear from you, I'm going to assume you're not taking it or you're okay with the standard timing. Okay, so if that's not the case, please get a hold of me and get a hold of me before Monday if possible, because otherwise that can be a little, I might have a tough time with turnaround. Okay, so other things about the final exam, it is going to be cumulative. So there'll be a little bit from everything, but it'll be a little bit more heavily concentrated towards the end. In terms of stuff that's out there, like your homeworks and exams and things that I haven't finished grading, I will get to that and have it all in by Friday so that you'll have an up-to-date idea of where you stand at that point. Excuse me. And I apologize for the delay. I already don't like grading, and in this Eve format, grading is even worse. It's more time intensive. It makes me want to like smash my head into the computer. So I've been dragging my feet, and that's unfair to you, and I apologize. But the reality of the world right now is that that's super low priority. And anyway, but I will get all that done by Wednesday so you know where you stand. So lab on Friday, we're going to go ahead and just not do lab. We're going to call it good because at this point, I know nobody really cares. And I don't either. So, and you do lose a lot not being able to experience it in person. And this one especially is more of a, you kind of need to be there to get something out of it. So otherwise, I'm just telling you numbers. There's not even anything fun to see, you know, like when we did standing waves and stuff like that. So that means that in terms of everything, you just have a couple more homework assignments that you need to make sure you finish up. And then the final, if you need to take it or if it's optional. If you're curious and you're not really sure if you're eligible after I get everything in, just shoot me a quick email or pop into an office hour and I can let you know. Because I don't want anybody to get caught by surprise, be thinking, oh, great, I don't have to take the final, and then opt not to, but you did, and then you get the 0, right? I don't want that to happen to anybody. So if there's any question, or even if you just want confirmation, just send me a quick email and just say, I think I'm good for the final. Is that, you know, not having to take the final, is that true? I'll reply and either confirm or correct if necessary. All right, so in terms of my side, that's everything that I have to share regarding where we are and what's going on. Any questions, comments, concerns on your end for you guys? Okay, well, hearing none, then we're going to go ahead and wrap up, but just want to let you know that it's been a fun quarter, or at least as fun as it can be. I'm actually pleasantly surprised with how it went. When I was first told how this was going to go, I was fearing the worst, but it worked out pretty well. So again, thank you guys for keeping coming and being interested. I especially love all the crazy questions because that's what makes science fun, right? Is looking at all these weird, wacky things and trying to explain it. And so thanks for being part of this. And if I don't see you guys the rest of the quarter, have an awesome summer. And, you know, who knows when I'll actually see you guys in person next. But, you know, it will be someday. And I don't know if anybody's graduating this year, but if you are, I know graduation is not officially happening as a graduation ceremony, but we're going to have sort of the kind of, I'm going to call it the parade of legends, just for lack of a better thing, right? Where you're coming and driving through to get your diploma and stuff. I will be there cheering on from somewhere along the road. So I'll be looking for you, but other than that, you guys have a great summer, and don't hesitate to reach out to me at any point if you have questions or anything. All right. So with that, I will say a final adios.
Thanks,
Later,
Bruce.
Bruce.
All right. See you guys.